End-of-day, EOD, processing logic in banking. We will learn how banks process transactions and balances at the end of each day. End-of-day logic is crucial for accurate account balances, interest calculation, and regulatory reports. You will build Python tools to mimic real-world end-of-day processing using synthetic banking data. By the end, you will know how to summarize transactions, calculate balances, and spot possible issues. Running the cell now. We import pandas for data handling. We import NumPy for numerical computation. We import warnings to manage library warning output. We turn off unnecessary warnings for a cleaner notebook. We set the random C to 42 for reproducibility. Running the cell now. Understanding the data for EOD processing. We will use sample banking transactions, customers, and accounts. Transactions record debits and credits by customer and account. Accounts link to customers and types such as savings, check, and credit. Common pitfalls include incorrect grouping, missing timestamps, or misclassified transactions. Running the cell now. Let us set up synthetic banking transactions to practice on. We define the number of transactions. We define the number of customers. We create a new data frame for our transactions data. We generate unique transaction identifiers. We randomly assign each transaction to a customer. We generate transaction amounts sampled from a normal distribution. We randomly assign each transaction as debit or credit. We pick a random channel for each transaction. We generate hourly timestamps for each transaction. Now our data frame DF is ready with all fields populated. We print the shape of the data frame to check its size. We preview the first 3 transactions to understand the data. Running the cell now. This output shows our synthetic transactions data frame with 1,000 records and 6 columns, confirming the dataset size and structure. Notice the key fields like transaction_ID, customer_ID, amount, transaction_type, and timestamps in date, which are essential for linking transactions to customers and understanding their timing. This validates our initial data setup, ready for exploration and identifying common pitfalls like missing timestamps or misclassifications. Try changing n_transactions and see how the output changes. Now let us make a table of customers, with some basic segment and region information. We generate a list of all customer IDs. We start our customer data frame. We save all customer IDs to the data frame. We assign the first 150 customers to retail and the last 50 to business. We set the first 100 customers as metros and next 100 as regional. Now the customer's data frame is complete. We print its size. We preview the first 3 entries. Running the cell now. The output shows a data frame with 200 rows and 3 columns, customer_ID, segment, and region, which confirms the creation of a sample customer dataset. Notice the first few customer IDs follow a consistent pattern, and the segments and regions are distributed as specified. This structure sets a clear foundation for linking customers to their transactions and accounts in subsequent steps. You can tweak the mix of segment and region to test new ideas. Let us add a synthetic accounts table. Accounts belong to customers and have types and open dates. We create a new data frame for account data. Each account receives a unique account identifier. We associate each account to its customer ID. We randomly assign account types as savings, check, or credit. We create a series of account open dates. Now our accounts data frame is complete. We check the size of the data frame. We show the first 3 rows. Running the cell now. This output shows the accounts data frame with 200 records and 4 columns, confirming our sample includes multiple account types linked to customers. Notice the consistent date intervals for account openings and the unique account IDs, which will help us properly group and join data in subsequent steps. This setup ensures we have a realistic, structured dataset for exploring transaction activity by account type and customer. Verify that each customer has only one account here for simplicity. Beginner Example 1, Daily Transaction Counts. A simple end-of-day check is to count the number of transactions per day. This shows overall banking activity and helps detect spikes or outages. Running the cell now. Let us count the transactions for each day. We group transactions by date and count them per day. We print the first 3 days' transaction counts. Running the cell now. Here, the output shows the daily transaction counts over the first 3 days of 2024, with a consistent count of 24 transactions each day. This confirms stable banking activity without any spikes or drop-offs, fulfilling the lesson's goal of using a simple end-of-day check to monitor overall transaction volume trends. Can you list the dates with the highest activity? Beginner Example 2, Daily Totals for Debits and Credits. End-of-day processing checks that money in and out is tracked daily. Let us summarize daily totals by transaction type. Running the cell now. Now let us break down daily debit and credit sums. Group by date and transaction type, sum the amounts, then reshape to compare debit and credit. Print the first 3 days' debit and credit totals. Running the cell now. Here we see the daily totals of money going in, credit, and out, debit, for the first 3 dates, which is essential for end-of-day processing. Notice how the data is grouped by each date and transaction type, then summed, giving a clear, easy-to-compare summary of funds moved each day. This helps ensure that all transactions are accounted for and balanced daily. Try plotting daily credit and debit activity for extra insight. Beginner Example 3, Find missing transaction days. Sometimes no transactions are recorded on holidays or weekends. Missing days can cause confusion or errors in end-of-day routines. Running the cell now. Let us find which days have no transactions at all. We create a full list of calendar days in the dataset. We pull the list of actual transaction days. We compare and find any days missing from transaction log. See the first 5 missing days, if any. Running the cell now. Here, the output shows an empty list, meaning there are no missing transaction days within the date range. This confirms that every day between the earliest and latest recorded dates has at least one transaction, which helps ensure our end-of-day routines won't encounter gaps or errors due to missing data. Review missing days, and think about why there might be no transactions. Intermediate Example 1, End-of-day account balance calculation. End-of-day balance is a core step in all account processing. For each account and day, calculate the running balance. Running the cell now. Let us now walk through daily account balance calculation. We give debits a negative sign and credits positive, for balance math. We merge transactions to account IDs for correct grouping. For each account and day, we sum the signed amounts and compute running daily balance. We reset the index to make the results easy to read. We print 5 daily balances to check. Running the cell now. This output shows the end-of-day, EOD, running balance for account ACC_00001 over several dates, capturing the cumulative net effect of credits and debits on the account. Notice how the balance changes day by day, reflecting the sum of signed transactions per date and the ongoing total, which confirms the success of grouping by account and date before applying the cumulative sum. This validates the code's intent to track each account's balance progression through time. What would happen if you forgot to give debits a negative sign? Let us show the last EOD balance for each account. Group by account and collect only the last EOD balance, then sort by highest balance. Show the top 5 account balances. Running the cell now. This output shows the latest end-of-day balance for each account, sorted from highest to lowest balance. Notice how the Group B, account_ID, .tail1, extracts the most recent balance per account, which is key to summarizing current standings. This step is essential for understanding account positions at the end of each day in the balance calculation process. Whose accounts have the highest balances at the end of the data set? Intermediate example 2, interest accrual at end of day. Banks often calculate interest at end of day, especially for savings accounts. We will estimate interest on balances above $1,000. Running the cell now. Let us calculate daily interest for positive balances over $1,000. We set an example annual interest rate, divided by 365 for daily calculation. Copy the EOD balances so we do not overwrite the earlier data. Compute interest only where the balance is over $1,000. Show the account ID, balance, and daily interest for the first 5 rows. Running the cell now. This output shows the first 5 rows of account balances with their corresponding interest calculated at end of day. Notice that all interest values are 0 because these balances are below the $1,000 threshold set in the code. This confirms the code correctly applies interest only to accounts with balances above $1,000, illustrating conditional interest accrual as intended. How does lowering the interest rate change overall payments? Now we sum up total interest paid per account over the data period. Aggregate daily interest per account for the whole time period and sort by best results. Display the top 5 total interest values. Running the cell now. This output shows the total accrued interest per account, summed across all end-of-day entries, sorted from highest to lowest. Notice that only account ACC_001 for earned interest above 0, indicating it had balances consistently above $1,000, while the others did not meet the threshold to accrue interest. This confirms our code accurately identifies and sums interest only for qualifying balances, reinforcing the concept of conditional interest calculation at EOD. Which accounts generated the most daily interest? Intermediate example 3, suspicious transaction patterns at end of day. End-of-day systems must flag suspicious transaction spikes for review. Let us mark days where a customer makes more than 4 transactions in one day. Running the cell now. Now let us identify suspiciously high daily activity. Group by customer and date, and count their transactions. Flag days with more than 4 transactions for manual review. Show a few flagged cases for demonstration. Running the cell now. The output shows an empty data frame, meaning no customers made more than 4 transactions on any single day in this dataset. This confirms that the code correctly identifies and flags only days with suspicious transaction spikes, and here, none meet the threshold. It's important to note how grouping by customer and date aggregates daily transactions, which is key for effective end-of-day fraud monitoring. Can you try adjusting the threshold to make the filter stricter? Advanced example 1, end-of-day region-wise consolidated balances. Banks aggregate customer balances by region for reporting and liquidity management. Let us summarize final end-of-day balances by customer region. Running the cell now. Let us merge account info with customer region and sum balances. First, merge last account balances with their customer IDs. Then merge with customer region information. Group by region and sum the balances for each region. Print the region-level balances. Running the cell now. This output shows the end-of-day consolidated balances grouped by customer region, highlighting a negative total balance in the metro region and a positive balance in the regional area. Notice how the code merges account and customer data first, then aggregates balances by region to provide a clear summary for liquidity management. This approach helps banks quickly see regional balance trends critical for strategic financial decisions. Which region holds more assets in this simulation? Advanced example 2, end-of-day closure file generation. End-of-day systems normally write daily closure files with balances and summaries for audit. Let us export the end-of-day balance data for compliance review. Running the cell now. Let us save the final account EOD balances for the period to a CSV file. Set the closure file name. Export the latest EOD balances to CSV. Confirm the file has been created. Running the cell now. This output confirms that the end-of-day account summary has been successfully exported to a CSV file named ed_closure_sample.csv. This step is crucial in the EOD closure file generation process, as it ensures the daily balances and summaries are saved in a standardized format for compliance and audit purposes. Notice how the code writes the data without the index, making the file cleaner and ready for external review. Now opening the daily closure CSV file so we can check its contents. Try reading this file back into Pandas for a quick sense check. Error handling example: invalid or duplicate transactions. End-of-day processing should catch errors such as duplicate transactions or invalid amounts. Let us check for negative or zero transaction amounts and duplicate IDs. Running the cell now. Now we flag invalid or repeated transaction records. Find all transactions with zero or negative amounts. Find and count transaction IDs that appear more than once. Print the number of rows with invalid transaction amounts. Print the number of duplicate transaction IDs. Running the cell now. This output shows that there are 7 transactions with invalid amounts, 0 or negative, but no duplicate transaction IDs were found. This confirms that our error-checking logic correctly identifies problematic amounts while ensuring transaction IDs are unique, which is essential for accurate end-of-day processing. Try adding a negative amount to your synthetic data to see error handling. Let us clean the transactions to remove errors before end-of-day calculation. We explain this is the step to remove all records with errors from our data. Keep only rows with valid positive amounts and unique transaction IDs. Check the new shape to see how many records remain after cleaning. Running the cell now. This output shows that after filtering out transactions with 0 or negative amounts and removing duplicates by transaction ID, 993 valid records remain. Notice how the code ensures only clean, error-free data is processed at the end of day, EOD, which is critical for accurate reporting and downstream tasks. The shape confirms the dataset size has reduced from the original, reflecting the successful cleanup. Remember, data cleaning is always important before running EOD logic. Best practices and patterns for end-of-day processing. Always clean input data for out-of-range or duplicate values. Include audit steps such as logging and export files in your logic. Use clear group B and merge steps to avoid mixing up customer or account data. Separate code for transaction processing and reporting. Running the cell now. End-to-end mini problem: balance proof across days. Suppose auditors ask to prove that the closing balance for day N matches the opening for day N+1 for one account. Let us fetch one account's day-by-day balances and check for mismatches. Running the cell now. Let us verify that daily closing and opening balances match for one example account. Select the account with the highest ending balance. Collect its day-by-day balances and put them in date order. Create a new column for the previous day's balance. Check the difference between each day's balance and the day before. Print the first 5 days to compare. Running the cell now. This output shows the daily balances for one account, with the previous day's balance aligned next to the current day's balance, allowing us to see the day-to-day change, difference. Notice the first row's previous _balance is nan because there's no prior day, and each following row's difference quantifies how much the balance changed since the previous day, key for verifying that the closing balance on one day matches the next day's opening balance. This stepping through balances sets the foundation for identifying any mismatches in continuity during the audit. Scroll down and see if any jump in balance occurs with no matching transactions. Do not forget to visit our YouTube for more on end-of-day logic in practice. Congratulations! You have built an end-of-day processing engine. You tracked daily transactions, calculated balances, checked errors, and generated end-of-day closure files. Practice. Can you add more end-of-day checks, such as overdraft detection? For more banking Python tutorials, search YouTube for Finance Python EOD and subscribe to learn more. Running the cell now.